Hello students, Professor Nugent here. In this video we're going to discuss prediction and prediction intervals with heteroskedasticity. If we want to get a predicted value, we would do that as usual. Plug in the values for x of interest and you get the predicted value of y. However, if we have heteroskedasticity, we have to keep in mind that the prediction interval is a function of the standard error, and the standard error depends on the nature of the conditional variance. We can obtain the standard error of prediction the same way as we would with OLS, except that we will use WLS. So let's talk about how we will obtain the standard error of prediction so that we can get a prediction interval for our prediction of interest. Let's consider an estimated regression where we have y hat is equal to beta naught hat plus beta 1 hat times x1 all the way through beta k hat xk. And we're interested in a prediction of y0 for values of x1 equals c1 through xk equals ck. Then y0, or we can say a y naught, the population equation for this is beta naught plus beta 1 times c1 through beta k ck, which is equal to the expected value of y given x1 equals c1 through xk equals ck. We can rewrite this equation with the big star so that beta naught is equal to y naught minus beta 1 c1 minus all the way through beta k ck. And then so we can take this and plug this into the regression equation, where the regression equation is y equals beta naught plus beta 1 x1 plus all the way through beta k xk. So we can substitute equation 1 into equation 2 so that we have y equals y naught minus beta 1 c1 minus all the way through beta k ck plus beta 1 x1 plus all the way through beta k xk, and then collect terms on the coefficients so that you have y equals y naught plus beta 1 x1 minus c1 all the way through beta k xk minus ck. So we run a regression of y on x1 minus c1 through xk minus ck, and we obtain the estimate for y0 hat as the intercept in that regression, and the standard error of y0 hat gives us that standard error. We do this using WLS as we have been discussing in this chapter. So the estimate and the standard error come from the intercept of that regression of y on x1 minus c1 through xk minus ck, where we use WLS to estimate this equation. Now we also need the standard deviation to complete this to get a complete complete characterization of the prediction interval. We need the standard deviation of u0 which is the unobserved part of y0. Observe that the variance of u0 for x equals x0, the values of c, is equal to sigma squared h of x0, which implies that the standard error of u0 is equal to sigma times the square root h of x, where, and here we have sigma hat. Sigma hat is the standard error of the regression. Then we can characterize the 95% confidence interval, the 95% prediction interval, that 95% prediction interval is y hat 0 plus or minus t 0.025 times the standard error of e hat 0, where the standard error of e hat 0 is equal to the square root of the standard error of y hat 0 squared plus sigma squared hat, the estimate of the error variance, times h of x0. So that we have the standard error to reflect both the errors in the unobserved stuff plus the errors to reflect the error in estimating the parameters. This interval will be exact if the variance function is not estimated, so if we have not used feasible GLS. There is a high potential for the estimation error in the parameters to be swamped by the errors in the unobserved stuff, so that this first term could be completely swamped, much smaller than the second term. We know that this first term gets smaller and smaller with sample size, but the second term is relatively constant. So the unobserved stuff could be really the most important part of the prediction interval.